Okay, let's now get started. In the previous session, Wilma, you're not in the previous class. So I will help you through with what has been covered. So in the last session, let's have a quick recap of what we had introduced. So in the previous session, the last thing we did talk about was dealing with limiting factors. So we did talk about dealing with limiting factors. So the first thing that you need to understand is what is a limiting factor. So if we are producing, a limiting factor is a resource which is stopping us from achieving the results that we want. It could be the material is not enough. It could be the labor. Maybe we do have the customers, but the labor hours are in short supply. Maybe the workers, we don't have enough workers. So it could be labor that is a limiting factor. It could be the machine time that is a limiting factor. It could be the factory space. So there are quite a number of factors that can act as limiting factor. So a limiting factor, put in simple terms, is that which is stopping us from reaching the target that we want, from reaching the potential that we want. Okay, so we did also talk about if you're faced with the limiting factor, the decision is choose the decision that gives you the highest benefit from the limited resource. Which decision is going to give you the maximum benefit from the limited resource? So that's what we discussed about. Then the limiting factor, it can be either one resource that is limiting us. It could be just labor, it could be just material. So we can either have a single limiting factor or we can have a multiple limiting factor scenario. So if it's a single limiting factor, it's just one resource. So it's just one resource that is stopping us. It could be just material, it could be just labor. But if it's now a multiple limiting factor scenario, in a multiple limiting factor scenario, it means it's more than one resource. So the resource acting as a limiting factor is more than one resource. Okay, so we also did mention that we can have what we call a slack resource. That is the last thing we mentioned. A slack resource is a resource which is more than enough. So a limiting factor, the resource is in short supply, but a slack resource, this one is more than enough. We have more than what we require. So we have part of the resource which is not going to be utilized. So the slack resource is the amount of the unutilized resource. So let's look at a question maybe to demonstrate the some of the things we were discussing in the last session. So just have one small question to, let's look at this one. So the question is saying a jewel company makes rings and necklaces. So the rings are represented by R, the necklaces are represented by N. The resources available to the company have been analyzed into two constraints. So the resources available to the company have been analyzed and two constraints have been identified. So we have two constraints, labor and machine time. A constraint is something that is capable of affecting our production. So we are saying labor time and machine time are the possible constraints of the business. Then the question is saying, which of the following is or are slack resources? So remember, if a resource is a slack resource, we have more than enough. A resource that is acting as a slack resource, we have more than enough. So let's start with labor time. Okay, there's a part which I did not read, which is saying the management accountant has used linear programming to determine that we need 500 rings and we need 400 necklaces. So these are the units. So in terms of the rings, we need 500. In terms of the necklaces, we need 400. So in terms of the rings, we need 500. In terms of the necklaces, we need 400. So the question is then saying, determine which one is a slack resource. So what are we supposed to do here? We are told that 3R in this case, it means if labor time, they're saying 3R, it means for labor, each ring, it requires 3 hours. And each necklace requires 2 hours. So you can use this equation that they've given us. So the equation is saying if we add the hours for labor, for rings, plus the hours for necklaces, they should be less than 2.4. In other words, they are saying the maximum available hours for labor is 2.4. So we can then calculate. Can you quickly calculate how many hours do we need for these units? For rings, we have 500 rings, and for necklaces, we have 400. So you can say 3 times 500 plus 2 times 400. How much do we get? So we're just substituting. In place of R, you're putting 500. In place of N, you're putting 400. 2,300. So 2,300 is what we need in terms of labor time. So we are saying for labor time, to produce the units given, we need 2.3. But how many hours do we have? We have 2.4. So we have more than enough. So this one, yes, we can confirm there is a slack resource. Because if we have a slack resource, we have extra. So we have a slack, it means we have extra resource. So labor time, yes, there is a slack. We have more than what we need. Now let's go and check for the machine time. Just do the same procedure for machine and confirm if there is a slack. If we do the same for the machine, what are we getting? So if we do the same for the machine, what are you getting? 410, but we have 410. So the inequality is saying that the hours we have for machine time cannot, they should be less or equal to 410. So meaning the maximum available hours is 410. So in this one match, we are saying that we need maximum hours available is 410, but the machine time needed to produce the rings and the necklaces is also 410. So it means the hours that we need are equal to the hours available. So there is neither a bottleneck nor a slack. So the hours needed are equal to the hours available. So it's not a bottleneck, neither is it a slack resource. So the question was asking which one is a slack resource, meaning we have more than the resource needed. So if there is a slack resource, we have more than the resource that we need. Now let's get moving. Let's now look at this was a single. This was just a demonstration of you determining whether a resource is a slack or it's not a slack. So now the next issue that we want to talk about is where we are faced with a multiple limiting factor situation. So it's more than one resource that is in short supply. So if it's a multiple limiting factor, this arises when there is more than one resource in short supply. A multiple limiting factor means there is more than one resource in short supply. So if we are determining, so there's more than one resource in short supply, we want to determine, so how many units should we produce with the available resource? We use what we call the linear programming method. So the resources that we have, they are not enough. Maybe labor is not enough for the units that we want. And as well, labor is not enough. And as well, machine time is not enough. So we can say that we are dealing with, we are producing two products. So we have two products, product X and product Y. So the products can be given any variables. You can use X and Y. They can give you product alpha and beta. They can give you any types of products in the question. But in most cases, if they give you the products maybe as, let's say, alpha and beta, we need to change them to X and Y. Why? Because the method we are going to be using uses a Cartesian plane, the X and the Y axis. So for you to be able to plot the information on the X and the Y axis, one of the product has to be your X, the other product has to be your Y. So let's say there are two resources. So we have labor time. Labor time is not enough. Like in the question that we did. So labor time is not enough. So if labor time is not enough, the first thing is let's determine how much in terms of, so let's say our budgeted plan was, let's say labor time per unit. You can say this one, product X uses 2 hours, product Y uses 3 hours. Then besides the labor time, we have machine time. This uses 4 hours per unit. This uses 3 hours per unit. And the hours available in total. Hours available. In this case, we can be told we have, let's say, 200 hours. Then we have, let's just say, 140 hours. Let's say we had units that we wanted to produce. We wanted to produce 300 units for X, and we wanted to produce 450 units for Y. So this is the case we are given. The plan is to produce 300 units for X and 450 units for Y. So if we say, if each unit of X is using 2 hours, if we say 2 times 300 already is above, it's more than the hours available. And the same goes with for machine time. 4 times, again, it's above the hours available. So with the limited hours available, how can we maximize the use of these hours? So how many units do we need to produce for X and how many units do we need for Y? That will help us to maximize profit. So that's what we'll be looking at if it's a multiple limiting factor. We're saying with the restrictions available in terms of the labor time is restricted, the machine time is restricted. How should we produce in order to maximize profit? The other constraint beside the time, we can be told that maybe demand. We can be told that the demand for product, let's just say for product Y, the maximum demand, let me put that one maybe as a statement. They can say the maximum demand, market research, of course we can produce 450, but market research is saying the maximum demand for product Y is 300, or we can say it's 320. Again, this is another constraint. So the constraints that we have, the labor time is not enough, the machine time is not enough, and even the demand itself is restricted. So in this case, we can say there is a multiple limiting factor. So there are steps that I gave you. Wilma, you're not there in the last session. Quickly jot down these steps. Quickly have these steps down. My example, let me just add as well, contribution. Contribution per unit. So this one could be 8 per unit. This one could be giving us a contribution of 10 per unit. Okay, you can quickly take down those steps.
Dancing.
Okay. So the steps are saying that the first thing you need to do is to define your variables. So define your variables. So defining your variables is simply telling us what is your X and what is your Y. In this case, we are already given X and Y, so there is no need to be defining the variables. But let's say we're given the product as a chair and desk. You would say let X be the chairs and let Y be the desk. You are now defining the variable to say what are you going to be using as your X and what is going to be your Y. So this is determining what is your X and Y. But there isn't one hard and fast rule really to say this one should be your X and this one should be your Y if you're dealing with limiting factors. So any factor can be defined X and any can be defined as Y. So now let's move on. After you have defined your variables, we then move on to the next step, which is contribution function. So coming up with the contribution function is the contribution equation. Contribution function. Contribution function. So the contribution function. So the contribution function, if we are looking at the contribution function, we are saying, or in other words, we can say the contribution function is the equation that will determine our contribution. Which formula can you use to work out your total contribution? So this is the equation we can use to determine the total contribution. So the contribution function is the equation we can use to work out our total contribution. The contribution function is the equation we can use to determine the total contribution. So, to determine your total contribution, we would say contribution is equals to so remember we're given the contribution for each unit. So the total contribution you're going to make will be determined by the number of X units we produce and the number of Y units. So for the contribution of X, you'd say the contribution per unit times the number of units. So you'd say that's 8X. So contribution is 8X plus. The contribution for Y is determined by the number of Y units, that's 10Y. So you'd say 8X plus 10Y. So this is the equation that we will use to determine the total contribution. So remember, if we are faced with a limiting factor, the decision should be the one that maximizes contribution. Or in other words, contribution is the benefit we are getting. So we need to choose a decision which will maximize the benefit. So this step is just determining, okay, how do you work out your contribution in total? So the contribution in total, you would say the contribution of X plus the contribution of Y. So let's now move from there. You need to determine the inequalities which define the possible outcomes, or we can say the constraints, the equations for the constraints. You need the equations for the constraints. So the constraints, these are the limitations that you have. So we need the equations for the limitations that we have. So which limitations do we have? The first limitation is that the labor time we use for X plus the labor time we use for Y should not exceed 200. That's the first limitation. So you would say 2X plus 3Y should not exceed. So this one is for labor time. 2X plus the 3Y should not exceed the available hours. The hours we use for X plus the hours we use for Y, they should not exceed the available hours. That's the first constraint equation we have. Then the second one is the hours we have for X plus for Y should not exceed 140. That is for machine time. So you would say the 4X plus the 3Y should not exceed, should be less or equal to the 140. It should not exceed the 140. Then lastly, the last constraint we can talk about is that of demand. So we are saying the units of Y that we sell, they should not exceed the units that are being demanded. So the maximum units of Y is 320. So we are saying This one is not affecting X. It's simply the units of Y should be less than 320. So we're just writing the constraints that we are given in the form of equations. Think of if maybe at O level, if you did linear programming, where you were drawing those inequalities and they were saying this should not exceed. So that's what we are saying also here. The amount of units you sell should not exceed 320 because that's the maximum demand. Then there is the non-negativity constraint. Non-negativity constraint, even if it's not given, you need to know that the units of X and the units of Y, they should be greater than 0. So if they ask you about the non-negativity constraint, this one is simply telling you that even if things are bad, you can't produce negative units of X or negative units of Y. Sorry, I can't put greater or equal. It can be equal to 0, but it should not be less than 0. So this means that the units produced cannot be negative. So this non-negativity constraint, it's saying that the units produced cannot be negative. The units produced cannot be negative. Now let's move on. So from there, we are done with the limitations we have. From there, we need to draw the graph and show the feasible region. But because now you draw the graph to show the feasible region. But now because it's computer-based exams, you will not find a case where there was a draw, but you need to be able to interpret the graph maybe that is drawn already. So draw the graph to show the feasible region. So what am I going to do? Let me find a graph that is drawn already. Then we just explain using that. So after you have your constraints, okay, this is how, maybe let's look at this graph. So using the inequalities, those constraints that we have, we could say this is the graph for the first constraint, because you'll be drawing, take note, this is a straight line graph. So if you are drawing the graph for the first constraint, for example, 2x plus 3y is equals to 200. This would give you a straight line. It's a linear equation. So you can use your maths knowledge to say, if you're drawing a graph, you can say when x is 0, you can use that concept of saying when x is 0, what is y? What about when y is 0, what is x? Then you use that to produce a straight line equation. So like I said, we're not going to dwell much on the drawing part because there are high chances the graphs will be there. So this could be the first graph of, say, labor time. This could be the graph of the other constraint, machine time. So that other constraint of demand, if they say, if demand y was just, remember this is your y-axis, so y was 320. This one, it will be just a straight line. At y is equals to 320. So it will be a straight line at y is equals to 320. So you'd come up with 3 graphs because you have 3 constraints. The non-negativity constraint, it's shown here because we are not dealing with the negative x. All the values you are given are positive values. So by virtue of doing that, it means our units cannot be negative. So after you've produced these lines, you need to do what? You need to identify what we call the feasible region. We need to identify the feasible region. The feasible region this is a region which shows all the possible outcomes. This is the region which shows all the possible outcomes given the constraints. We are saying, yes, there are constraints, but with these constraints, what are the possibilities? So yes, there are constraints. We can't produce all the units because labor time is in short supply, machine time is in short supply. But with what we have, what possibilities do we have? So it gives us a number of possibilities, not just one. So the feasible region is showing us all the possibilities. I think let me find another graph where I can, where we can see the feasible region. Okay, using this graph, let's say the one that we had drawn, the feasible region is supposed to be this one. Let's ignore the 60-60. I'll talk about it last. Let's think of these three lines, 1, 2, and the third one. So the feasible region is a region that is falling below all these lines. So like this region is supposed to be a region that is inside all these lines, ignoring that other line coming from 60 to 60. So the feasible region is this region that I'm shading. So if you look at this region, it's not above any of the lines. It's a region that is below all the three lines. So the feasible region, it shows us what is capable of being produced considering all the constraints. So this region shows that it's possible to produce so the region is showing that it's possible to produce anything below this. So it's showing that it's possible to produce anything below this. So you can produce 40 units for Y and produce 20 units for X. You can produce 40 units for Y, you can produce 40 units for X, as long as these are meeting within the feasible region. But the issue is not about us just producing within the feasible region. We want to identify the combination that will maximize contribution. Our resources are in short supply. The feasible region has shown us the possibilities. Now the issue is, let's identify which point will give us the maximum benefit. So at which point are we likely to get the most benefit? So we can say, after identifying the possible, after identifying all the units that can possibly be produced in the feasible region, that can possibly be produced in the feasible region, we need to determine which combination is the most profitable. we need to determine which combination is the most profitable. We need to determine which combination is the most profitable. So the combination which is the most profitable, how do we determine? Because there are quite a lot of combinations. If you can see from my demonstration here, there are a lot of combinations you can come up with. You can decide 60 for Y and 20 for X, 20 for Y, 60 for, as long as it's meeting within our feasible region, it's possible. So now to determine which one is the most profitable point, we use the ISO contribution line. Is it there on our steps? Let's check the steps. Feasible region, then the ISO contribution line, yes. So we use the ISO contribution line. So to determine the most profitable point, we use the ISO contribution line. We use the ISO contribution line. In most instances, the most profitable point is not on, so our most profitable point, we don't get it inside the feasible region. In fact, we don't get the most profitable point inside the feasible region, but we get it on the vertices, either here so we can get it here, on these corners, on the vertices. This is likely to be the points where we'll get the most profitable combination. So the most profitable combination should be the maximum units of X and Y that will give us the most benefits. So they will give us the ISO contribution line. In some cases, they will give you as a dotted line. In this case, I think 60 will be, this line will be our ISO contribution line. So this ISO contribution line, we push it outwards, maintaining the same gradient until there is only one point. Of these points that we've marked, the corners, we push it outwards until there is only one corner left. So if we push it outwards, maintaining the same gradient, it's likely that this corner is the only corner that will remain above the line. May I just answer? Hello. Seriously. Yeah, all right. Now that will go now to Maria. All right. Marugopia, Masangana, Madroxide. Okay, so it's the most profitable point is the one that will be the last to show on our ISO contribution line. If we are to push it outwards like this, the last point above the ISO contribution line from these corners, maintaining the same gradient. So it's most likely that this point. So we then get this point. So this point shows us the most profitable outcome. So it means for us to be profitable, we come to this point where these lines meet. You find what would be the value of X and what would be the value of Y. So this will tell you, so how many units of X do you need and how many units of Y do you need? Those are the units that would maximize your profit. But the points are not always given in a way that you can easily check by inspection. Like in this case, you can't tell by inspection which units of Y and which units of X, because the scale is from 40 to 60. So what do you do in such a case? You find which lines are meeting at this point. We find the equations of the lines meeting at this point. Let me rub off and so the lines that are meeting is this line and that line. So to find the units, if you cannot see them by inspection, you take these two lines, you solve them, you solve the equations simultaneously. So you solve them in simultaneous equation. That will give you what will be the value of X here and what will be the value of Y. So let's go to our example. So to determine the profitable point, we use the ISO contribution line. The last point to show on the ISO contribution line if it is pushed outwards. Maintaining the same gradient. Is the most profitable point. It is the most profitable point. We use the simultaneous equations. To determine how many units of X and units of Y to be produced at this point. However, if you can see it by just looking at, if it's maybe clear where these two lines are meeting, where you don't need to use simultaneous equations, you can just use the graph. So after you have determined, let me just come up with a rough estimation. So let's assume here it's 50. Let's just say there's 50 for Y, and I think 50Y, 50X. I think you can say 50 for Y and 50 for X. So we can say that point X will be 50 and Y will be 50. So, or let's say, maybe let's say X is 45 and Y is 50. So you use your simultaneous equations to get the actual values. So after getting your X as 45 and Y as 50, this means that with the given constraints, it is more profitable to produce, it is more profitable to produce 45 units of X and 50 units of Y. "45 units of X and 50 units of Y." But the question sometimes will not say just calculate the units. They will say determine the maximum contribution. So they will then say determine what would be the maximum benefit. Of course, to maximize our benefit, we need 45 units of X and 50 units of Y. But what is the contribution in terms of money? What benefit would we get? This is where we apply now the contribution function that we created, the 8x plus 10y. So the maximum contribution, we go and substitute for maximum contribution. So for maximum contribution, you then go and substitute. To get the maximum contribution, you then go and substitute into your contribution function. So the contribution function was saying contribution is equals to 8x plus 10y. 8x plus 10y. So you'd say your contribution is equals to 8. In place of x, now we substitute the units of x. So it's now 8, x is 45. 10, in place of y, we substitute 50. So what would be our total contribution? What? 860. So it means our contribution that we are getting, if we use that combination, it would be 860. That's the maximum contribution we can get. That's the maximum contribution we can get. Then the next part would be the shadow price. The shadow price. So the shadow price is the maximum price we can pay. This is the maximum price. This is the maximum price that we can pay for the additional unit of the limited resource. The maximum price that we can pay for the additional unit of the limited resource. What does this mean? We are saying labor time was a limiting factor and machine time was a limiting factor. Let's have a case maybe where someone says, okay, I can sell you my labor time. We can find someone who say, okay, they are limited. I can come and work for you, but I need you to pay because in the market right now, labor is a limiting factor. Everyone is looking for labor. So I can come and work so that we increase the number of units, but I'm offering you this much. So how much should we pay for that additional hour? That is that is now the shadow price. What is the maximum that we should be willing to pay? Because there is a constraint. Someone is willing to give us that resource that we need, but how much should we pay for the extra units? So we can say, they can say, what is the shadow price? Looking at our question then, they can say, what is the shadow price? What is the shadow price for, what is the shadow price for labor time? What is the shadow price for labor time? So to get the shadow price for labor time, we go to our simultaneous equations. Let's say these were the equations that gave us 45 and 50. So 2x, so we can say equation for labor. Equation for labor time was 2x plus, was it 2x plus 3y? 2x plus 3y is equals to 200. So if you're now putting it as an equation, we just put equals instead of the inequality. So 2x plus 3y is equals to 200. That was the equation for labor time. Then the equation for machine time was 4x plus 3y is equals to 140. Remember, we made an assumption there that the 45 and the 45 and the 50 were not the actual. So that was an assumption. So now, the shadow price, we are saying, if we are to add one additional hour, maybe let's start by this one. I think it's an easy simultaneous equation. Why? Because we have 3y and 3y. So let's first of all calculate the actual thing. Sorry. So let's first of all calculate the actual thing. So let's calculate the current units of x and y. Not those ones we just, let's calculate what would be the units of x and the units of y. So you can use the elimination method, you can just subtract. Hopefully, quickly work that out. Okay, are you done? So what's the value for x? But x is what? Negative 30. So if it's giving us something like that, I think our assumption was all right, because remember our units for x can be negative or either y. So let's say before the 50 and the 45, those online, are we still together? So far, are we together? Any questions?
No questions. I'm following up.
Okay. So the shadow price, we are saying, if we are to add, remember labor time, they can say, what is the shadow price for labor time? So we are saying if we add 1 extra hour for labor time, there were 200 hours. If we add 1 extra hour for labor time, if we add 1 extra hour for labor time, if we add 1 extra hour for labor time, how is going to be the contribution affected? So in this case, would repeat the same equation for labor time, but adding 1 extra hour. So it would be, so if determining the shadow price, for labor, we add 1 extra hour for the labor. We add 1 extra hour for the labor. Sorry? It's all right. We add 1 extra hour for the labor and determine how the units will be affected. We add 1 extra hour and determine how the units will be affected. So in this case, we would recalculate the equations. We would recalculate the units of X and the units of Y, but the equation for labor time is going to change. The equation for labor time is going to be 2X plus 3Y is equals to, instead of 200, now there's 1 additional hour, is 201. Then the equation for, because we've added 1 hour for labor, it means the time for machine is not changing. We just add 1 to labor hours. So the shadow price is, if we've added 1 extra hour for labor, how is the contribution going to be affected? So in this case, let's assume, it's again an assumption because remember the equations I gave as random equations. So for X, let's assume it was, for X, it was 45. If we add 1 extra hour, so assume for X it's going to be 44, and for Y is going to be 52. So for X, 44, for Y, 52. That would be the new outcome. So to determine the shadow price, you substitute. We are now substituting the new equations. So we are now substituting the new outcomes into our contribution equation. So let's go and substitute these outcomes into our contribution equation. So our contribution equation was 8x plus 10y. Now we are substituting the new outcomes after we've added 1 hour for the labor time. So our new contribution would be, it was 8x. So in this case, it's now 8 times 44 plus, it was 8x plus what? 10y. So in place of y, we're putting 52. So what would be our new contribution? Is it 9 or 8? 872. So our new contribution is now 872. What does this mean? So it means It means that if we add 1 extra hour for labor, our contribution is going to increase from 860 to 872. So the shadow price now is the shadow price. We are now going to say the change in contribution 872 minus 860. So the shadow price was 872 minus 860. It's 12. So we are saying if we hire their labor for every hour, our contribution or our benefit is going to be $12. So the shadow price is then saying they can't now charge us a price above 12 because that's the maximum benefit we get from their additional hour. So their rate per hour should be less than 12 for us to remain with the benefit. Because if they are saying, okay, labor is in short supply, so I'm going to be charging you $15 per hour, we'd rather say no. Why? Because our maximum benefit for the additional hour is $12. So the shadow price is calculating what is the maximum benefit we're getting, which is also the maximum price we should be charged for the additional hour. Because once they charge us anything above 12, we are now making a loss. So the maximum price we should be charged. We should be charged is $12. And of which, if we get the labor at $12, we won't be making any profit. We'll be breaking even because the additional hour is giving us $12. So to be profitable, we should actually charge lower than 12. We should be charged lower than $12. So that is the multiple limiting factor. So those are the key issues if you're dealing with a multiple limiting factor situation. Let me just show you, or let's look at it. Let's quickly look at the question. Where we can apply that, then we move to the next topic. Okay, I think this diagram is explaining better. This diagram is explaining better. So for this diagram, they've given us material A equation, machine hours equation, direct labor hours. So they've given us the constraint equation, and the ISO contribution line they've noted is being shown by a dotted line. And they've mentioned A, B, C, D is our feasible region. So point A, from point A, we go to point B. From point B, we go to point C, D. So this is our feasible region. This trapezium here, that's our feasible region. Then note that DL is direct labor hours. Point marked B, this point B, has been determined to be the point which provides the optimum production time. So that is our point where we would maximize the contribution. So which of the following resources will have a shadow price greater than 0? Which of the following points would have a shadow price greater than 0? So if direct labor hours, material A, material B, machine hours. So remember the shadow price is the additional benefit we get from every hour. So the shadow price, let's go to the diagram and see what how we can interpret that with the. So let me read the question again. Which of the following resources will have a shadow price greater than 0? Select all that apply. A shadow price greater than 0. So remember, we say the shadow price, if we add 1 additional hour, then we want to look at the I'm thinking all the points, because the shadow price, it should be for those resources that are the constraint resources. So the resources which are lying in our constraint, sorry, let me mark the resources which are lying on our constraint. So our point, our optimum point is that one. So we have the equation, this equation, and this equation. So these are our constraint equations. So these are our constraint equations. So the shadow price is if we add 1 additional resource of the constraint equation. So I'm thinking we just confirm this one. It should be this R500 and machine. So that's machine hours. This one I'm not getting the question. We check. We'll confirm with the answers there. I want a paper, a section C type of a question. Let's say shadow price. Hmm? Some of this looks like these are solutions. Let me check which one is this for. Mama questions on con. Let me check on Ama solutions. Yeah, I meant something like this. So the question here is saying, find by appropriate calculation the optimum production mix and related maximum contribution that could be earned. Then part B is saying calculate the shadow price of the fabric per meter and the tailor time per hour. So this would be the case. So they will give you the diagram already. So let's read the question and see where it's coming from. So you can quickly read through the question. Okay, so cut and stitch makes two types of suits using skilled tailor's labor and a delicate, unique fabric. Both the tailors and the fabric are in short supply, and so the accountant at CS has correctly produced a linear programming model to help decide the optimal production mix. So there is a short supply here of two resources, which is the skilled labor and also the material. So we are told the model is as follows. Let W, so that's defining the variables. They did not use X and Y, they used W and L. So let W be the number of work suits produced. Let L be the number of launch suits produced. Here's one. Then from there, we move on to the constraints. The constraints is what limit us. The constraints is what limit us. So they've done the constraint equations for us. 7W plus 5L is 3.5. This is now similar to that stage where we're saying 3x plus, is it 2x plus 3y is less than 200. So they've done that stage for us. So they've given us three constraints: the tailor's time, the fabric, and the production of worksuits. Then they've given us the objective function, which is the contribution equation. C is equals to 48W plus 40L. Then, on the diagram provided, the accountant has correctly identified OA, B, C, D as the feasible region and point B as the optimal point. So, having this diagram, they've drawn the diagram for us. Like I was saying, Kuti, there are chances for us they can't say draw because it's now computer-based. So they'll give you the diagram, but there's need for you to be able to interpret it. So given in dotted lines is most likely to be, so they've given us the feasible region, A, OA, B, C, D, and the optimum point. The optimum point is the one that maximizes our contribution. So we're not choosing for ourselves, but even if we're doing it ourselves, we would push the contribution line, that one in dotted, would push it outwards. So the ISO contribution line would push it outwards. So point B is our optimal point. So meaning at B, this is where we would maximize our profit. So they've done most of the work for us. So what is it that they are asking? So find by appropriate calculation the optimum production mix. So it means they want us to determine the mix is the number of units for W and the number of units for those W and L. The number of units for W and number of units for L that we need to produce. So it means you're coming here, you determine how many units this side and how many units this side. But again, you can't see this by inspection. So remember what I said. If you can't see it by inspection, determine the two equations that are meeting there. So we have equation T and equation F. If you go back to the question, they'd given us the equation for T, this one. And they'd given us the equation for F. So you are working out these two simultaneously. Can you do that? Can you work the two simultaneous equations, but you're using W and L instead of X and Y? Can you quickly solve that, please? To determine how many units of W and L to produce. So that's what the question is asking, the optimum production needs. Are you done? Okay, Wilma, are you done? So Amy, what did you get? So W is 250. Then L W is 350, L is 250. Sorry, W is 250, L 350. So that is our shadow. Sorry, no shadow price, sorry. That is our optimum production. Then the next part of the question is saying, determine the shadow price. Online, are we together?
Yes, sir.
Okay. So now we're moving to the next step. The next step is determining the shadow price. So shadow price is saying, calculate the shadow price of the fabric per meter. There are two shadow prices that you need, prices. In fact, it's saying prices. So shadow price for fabric per meter, you're going to the equation that they've given us, and you add for fabric per meter, which is the equation for fabric. For fabric is the second one. So you add 1 meter. So it becomes 1.201. Then you calculate your shadow price. Then if you're now calculating the shadow price for Taylor's time, you go back to the original equations, you add 1 hour for the Taylor's time. So you're not adding 1 both sides. So it's add 1 first for fabric, then you calculate. Then you add 1 first for the Taylor's time, then you calculate. So we're not yet done with the question A. Question A had said also and the maximum contribution. So before we get to the issue of shadow price, can you then work out what is the maximum contribution? So you're done with the maximum contribution, right? Now, can you work out the shadow price? Can you go to the equation of Taylor's time, you add 1 hour and calculate your shadow price? You do the same for fabric time, you calculate your shadow price. Let's quickly please finish up so that we can look at other things. After this one, we are now moving to the next topic. We need to just check that last question, check it is number one. Life ones as a shadow price. Okay, are you done with even any of them so that we just confirm? So what are you getting as your, so let's start from the contribution. So you'd say the contribution is what? Was what? 40W, 48W plus 40L. So it's just a matter of substituting. So for W, it was 250 plus 40L. L is 350. $26,000. So that's our contribution. So shadow price. So just do for one. So the shadow price, we want to check the increase in contribution. So check the first equation was what? The first equation, even any? For fabric, it's 2W plus 2L is equals to 1,200. Then the other one, 7W plus 5L is equals to 3,500. So shadow price for fabric, it means you're going to add 1 hour for fabric. So it would be 2W plus 2L is equals to 1,201. Then the second equation is not going to change. 7W plus 5L is equals to 3,500. So what would be the value of W and L? After adding 1 hour of fabric. So let's quickly do it together for the sake of time. So we are saying if we are using the simultaneous equations, if it's maybe the elimination method, so we can multiply everything on top by 7. So that's 2W, or let's just do it. So 7 times 2, that's 14. 14W plus 7 times 2, that's 14 again. L is equals to what's 1,201 times 7? 8,407. Then the equation below, we multiply everything by 2, we get 14W plus 10L. 14W plus 10L is equals to 3.5 times 2, 7,000. Then using the elimination method, 14 minus 10, that's 4. 4L is equals to what's 8,407 minus 7,000? That would be 1,407. So you divide both sides by 4. What would be the value of L? Dividing both sides by 4. So L is 351.75. Then W, so you just substitute in any of the equations. In place of L, you put 351.75. So you can take even the original equation, 2W. So we're saying 2W plus 2L. So in place of L, we are putting 351.75. So what would be our value for W? 2W is what? 248.25. So now can you recalculate the new contribution using these new values, new contribution? So the new contribution using the new figures. $25,986 like this. So our shadow price, we are now looking at the contribution. So does it mean the contribution is actually reduced? So from 26,000, so the new contribution is actually lower. So the shadow price so in fact there isn't a shadow price cap because the contribution is actually now less than, so they can't even charge, because adding one additional hour, it means we are actually getting less contribution. Unless if there was a mistake there in calculation. Let's go and check on their answers. So this is question number what? $286. It's 280, so let me. Which one is this? I think it's this one, right? So for A, 26,000. So for A, 26,000, we are in agreement, right? Then for B, the equations, or they started with T. For F, how come our answers are different here? It's okay. So I think it was the issue of solving the simultaneous equation. Okay, anyway, let's move. So I think it was an issue of solving the simultaneous equation. Let's just confirm the idea. So you can check. They are saying, what is their conclusion here? So the conclusion here is contribution end at this point would be, if we are to add 1 hour, the contribution would now be 26,010. So it means the contribution has increased by 10. So the shadow price is 10. Let's move to pricing. Let's move to pricing. pricing. So the price is this is the value we are charging to our products. So for us to be able to charge a certain price, we need to, first of all, determine a number of factors. So the price, this is the value. Allocated to the product the firm is selling. The value allocated to the product the firm is selling. So the organization can have different pricing strategies because the price that we charge, it will determine the profit that we make. It will determine the market share that we are going to have. So there are different strategies that we can use depending on what is the objective of the company. So if our objective is to maximize market share, then we can use what we call penetration pricing. Pricing strategy. So if it is the penetration pricing strategy, you start with low prices so that you can penetrate the market. So the firm starts by charging low prices so that it can penetrate the market. So we start by charging low prices so that we penetrate the market. Then besides the penetration pricing strategy, we also have the opposite of penetration, because penetration, it starts by, it's normally for a new product in the market. We start with very low prices with the assumption that as long as things are cheap, customers are going to buy. So if we start with very low prices, it's going to be perceived, however, that the quality is also low. So it will not attract a certain type of market. People will associate your products with poor quality. So we can choose to start with the skimming strategy. Skimming pricing strategy. So if it is the skimming pricing strategy, we are starting initially with the high prices. So we initially charge high prices with the assumption that as long as the products are charged high prices, customers will believe they are also of high value. Also, they are also of high quality. So they assume that anything that is expensive is of high quality. So we initially charge high prices. In order to send the message that the price, the firm's products are of high quality. So if it is the skimming strategy, we are initially charging high prices with the aim of communicating to our customers that this is of high quality. Then besides the skimming pricing strategy, we also have, so besides the price skimming, we also have the cost plus. Which can be further broken into, it could be marginal cost plus or full cost plus. This is the commonly used pricing strategy. So you calculate the cost that you have incurred. Then on top of those costs, you add a profit. So this strategy adds a profit on top of the costs incurred. So we calculate how much are the costs. It could be all the costs, which is full cost plus, or it could be marginal cost plus. But the idea behind, we first of all calculate the cost, then we add a profit. So this strategy adds a profit or a markup. This strategy adds a markup. adds a markup to the cost of production. So we are adding a markup to the cost of production. So if we are adding a markup to the cost of production, it could be either to the full cost. Full cost, it means we've included both the variable and the fixed cost. Let's think of a tuck shop scenario. In a tuck shop, we normally use markups, markup plus or contribution pricing, where we just consider the variable cost. Why? If you're charging a price in a tuck shop scenario, you can't include the rental cost in that price. You want to charge maybe the price for cooking oil. We can't include, you can, of course, you do consider what was the purchase price. You bought it at how much, but you don't include the cost of rent, the cost of salaries and wages. You don't include that in your price. So it's just the marginal cost. You don't take into account all the costs. So if it is the full cost plus, you are taking into account all the costs, then you add a profit. Then besides the cost plus pricing strategy, we can also have price discrimination. So if it's price discrimination, we are saying for the same product, we are charging different prices. If it's price discrimination, different prices are being charged for the same product. It could be, we can discriminate based on location, we can discriminate based on time. So the same product is being charged different prices. Product or service is being charged different prices. This is ideal, especially for services, but for goods, it can be tricky. We have to make sure the markets are far away from each other, because if there's a close distance between the markets, people can buy where it's cheap and resell in the markets where it's expensive, because a product is the same. But for a service now, because of the characteristic of a service that you cannot retail a service, it's possible to discriminate. It's possible to discriminate a service, because I can say, if I'm going to charge in town, I will charge a higher price than the price that I can charge if I'm maybe teaching, let's say, in Chitungwiza. But no one can go and buy what I'm teaching in Chitungwiza and resell it in town, because it's a service. So price discrimination, it's possible for us to discriminate services in most cases, but for products, it's a challenge. Then we can also have competitive pricing. So we can lose the price that is being charged in the market. Watch what your competitors are doing. You charge your prices based on competitor behavior. So the prices are charged based on competitor behavior. So you may charge the same price that the competitors are charging, or you can maintain your prices maybe at a certain percentage below your competitors. So if your competitors change their prices, you also change, but based on the competitive price. Then we can also have complementary pricing. So there are complementary products that you have to consume at the same time. Let's think of you buying a car and fuel. So once you have a car, you need fuel. So we can lower down the price of a complement. So we lower down the price of cars and we make it fuel expensive. You know, once people have cars, they are forced to buy fuel. So that's complementary product pricing. So we lower down the price of the one complement and increase the price of the other. So we've lowered the price of one and increased the price of the other. So let's move on. But there are also even other pricing strategies, such as psychological pricing strategy, where we can charge prices where you can find in other shops it's going for $100 and they are charging $99.99. So some might actually think maybe since this is at least I'll be saving something, but you're not saving anything if it's $99.99. If someone is charging 100 and you are being charged 99, you won't get 1 cent, 1 cent change. So that is. So now let's move on and talk about what is the optimal price. Or let's start from before we get to the let's look at the price and demand relationship. So price against demand, price and demand. So there is an inverse relationship between the price you charge and what the customers are going to demand. Once prices are low, demand tends to be high. So demand is high when prices are low. So if you want to increase the level of demand, lower down the price. If you want to lower down demand, increase the price. Then there is the price function, which shows us the relationship between the price and the quantity demanded. So the demand function shows us the relationship between the price and the demand. Says that the price P is equals to A minus BQ. P is equals to A minus BQ. So it says that the price, that's P, is equals to A so A, we can say this is the price when demand is zero. At what price will demand start becoming zero? So if you charge this price, no one will buy. So A, it is the price when demand is zero, where demand is zero. Then B, so B looks at the strength of the relationship of price and demand, or we can say is the gradient. So B looks at is the strength of the relationship between the strength of the relationship between price and demand. Then Q is the quantity demanded. Q is the quantity demanded. So the first case, we can give it we can say case one. They can say determine the price function or the demand equation. So determining the price function or the demand equation. Determining the price function or the demand equation. Determine the price function or the demand equation. If you are determining the price function or the demand equation, they will give you, they can say, the price okay, the price you can say when the price is $45, the customers prefer to buy, the customers prefer to buy 4,000 units. But when the price is increased to $50, demand falls. To 3,000 units. Demand falls to 3,000 units. What is the price function? Or what is the relationship between the price and the demand? So our price function in this case, we need to work out, if you are working out the price function, P is equals to A minus BQ. We need to work out our variables. So the variables, how do you work out the variables? You first of all determine the value of B. That is the first step. So you get your value of B. B is the change in price over change in quantity. So B, we are saying price changed by how much? It changed by 5. What about the quantity? The quantity then changed by 1,000. From 45 to 50, it's 5. From 4,000 to 3,000, quantity dropped by 1,000. So our B is 5 over 1,000, or we can say that's 5 over 1,000. That would be 0.005. After getting your B, you take any price together with its quantity. For example, you can take 45 on price. Then you say is equals to A, we don't know what's A, plus B. Now we have B is 0.05. Q, if price is 45, the quantity is 4,000. Okay, so if you had to simplify that, what do we get? You get 20. Yes. 20, then you take it that side. So it becomes 45 minus 20. That is equals to A. So 45 minus 20, that's 25. So our A is 25. Our A is 25. Then the price function, we go back to that equation. We say P is equals to A, that's 25. A, that's 25 plus our B. So in terms of our B, we are taking 0.005 Q. So it means what we are only changing is the value of A and value of B. In the price or final answer, in the function, we change the value of A and B only. So you are going to be removing the value of A and the value of B only. You're changing the value of A and the value of B. Okay, so now let's move on. So that's our price function. So from there, now let's move to, so this shows us the relationship between the price and the quantity. It's showing us the relationship between the price and the quantity. But now the question is, what is the optimum? Remember, we're looking at the optimum production plan in our limiting factor, where we're saying, what is the best combination of units that we should produce? So in this case also, we might be required to determine the optimum, we can be required to determine the optimum price. So at what price are we going to maximize profit? Because remember, we can use the price skimming. We can use, but if we use price skimming, demand will be low. If you use penetration, again, the prices will be low. So at what price should we charge if we want to make sure we are going to maximize our profit? So profit in pricing is maximized where the marginal cost is equal to marginal revenue. So the optimum production, also the optimum price, which maximizes profit, is when marginal cost is equal to marginal revenue. So optimum price which maximizes profit is when marginal cost is equals to marginal revenue. So what is the marginal cost? The marginal cost are the variable costs of the business. So the marginal costs are the variable costs of the business. So profit is maximized where the marginal cost or the variable cost of the business are equal to the marginal revenue. Profit is maximized where marginal costs are equal to marginal revenue. Then let's move on. If we are saying marginal costs are equal to marginal revenue, in most cases, they will not give us marginal cost, but they'll give us variable cost. So you should know that marginal costs are the same with variable cost. Then the marginal revenue, we have to calculate the marginal revenue. So there is an equation we use to determine marginal revenue. So our marginal revenue is calculated by saying A minus 2BQ. So this is what we call the marginal revenue equation. So that's our marginal revenue equation. So marginal revenue is equals to A minus BQ. That's our marginal revenue. Marginal revenue is equals to A minus 2BQ. So for our marginal revenue is equals to A minus 2BQ. What does this mean? So we are saying calculating A and B is the same thing. So in this case, our marginal revenue equation would be our A is 25 minus 2 times 0.05. 0.05 times 2, I think that would give us 0.01. So this is our marginal revenue equation. That would be the marginal revenue equation. So marginal revenue, we are saying at marginal revenue A minus 2BQ. Lisa? Marginal revenue is equals to A minus 2B. So I don't want to say anything wrong. I can find it. Let's move on. So marginal revenue, we're done. So the question will say, the question can say, just calculate the marginal revenue up to that. Sorry, the marginal revenue equation. That would be the marginal revenue equation. So what would be the optimum price? So the optimum price, let's say this is the case we are given. The optimum price, we don't know, because if we increase the price, demand is going to fall. So what is the price that would maximize our profit? Because increasing price increases profits. Increasing the units sold again, it also increases profit. So what is the best price? So the marginal, so now let's move on to calculating the optimum price. So the question will give you the marginal cost. They'll say calculate the optimum price when maybe the variable costs are, let's say, $80. So calculate, sorry, what were the price? Okay, let's say calculate the margin when the variable cost, let's say $28. Calculate the optimum price. When the variable cost $28. So to calculate the optimum price, remember we said at optimum price, marginal cost is equals to our marginal revenue. And we also said our marginal cost is the same as the variable cost. So you substitute. So in place of marginal cost, you put 28, that's your variable cost, is equals to your marginal revenue. So in place of your marginal revenue, you are putting your marginal revenue equation, which is 25 minus 0.01 Q. That's the marginal revenue. Then you first of all, using this equation, you work out the value of Q. So you can take Q this side becomes positive, take 28 that side. Again, I think 28 is too big. Again, let's reduce to 20 instead. So this would give us 0.01 Q is equals to 25 minus 20, which is 5. What is the value of Q? 500. So it means if you want to maximize your profit of maximizing quantity, we are not yet on the price. The quantity should be 500. You should sell 500 units. So the 500, this is your profit maximizing quantity. So that's the quantity which would maximize your profit. What about its price? To then get the price, we take the price function and substitute. Remember our price function that we calculated on A. So we take that price function, where we have Q, you substitute the 500. So to get the price, we use the price function. We use the price function calculated in A. The first one that we calculated, which is P is equals to 25 plus 0.005 Q. This was our price function. So we substitute the 500 into this function. What answer would we get? So if we want to maximize profit, reduce your price to 27 point. So reduce your price to 27. So let's look at a question on this, then we close.